Hello and welcome to this session. In today's session, we'll be studying the state transition diagram of 8085. So now that we have completed almost all the instructions of microprocessor 8085, we have also studied about the interrupts. We can complete the state transition diagram of 8085. We have been talking about different states in which the of 8085 we have T1 to T6, and apart from this you have T reset, T halt, T wait, and T hold. So you have 10 T states in total of 8085, T1 to T6, each being of one clock cycle, while as T reset, T halt, T wait, and T hold, they are of multiple of integral T states. So we know what T1, T2, T3, T4, T5, and T6 for different commands, for different instructions, for different machine cycles. We have seen what the microprocessor basically executes in T1 to T6 states, but we do not know what the microprocessor does in or how it enters or how it exits T reset, T halt, T wait, and T hold. Uh, these states. So first up, we'll be studying the T halt state. So how does a microprocessor enter T halt state? Uh, we have studied the instruction halt. This is one of the machine control. This is one of the machine control group of instructions, and we have executed this at the end of every program. The opcode of halt instruction is 76, and as soon as the program your program finish running, we basically make sure that the microprocessor the halt instruction is executed and the microprocessor enters the T halt state. So you can basically assume that a microprocessor that during an opcode fetch machine cycle, once it is initiated, the opcode is then transferred to the IR, that is the instruction register, and the opcode is basically transferred to the instruction register in the T3 state. And in this case, let us assume that we are talking about the halt instruction. So in the opcode fetch machine cycle of the halt instruction in the T3 state, the opcode is transferred to the instruction register, and it the instruction then becomes equal to 1, that is halt becomes equal to 1 in the T4 state of the opcode fetch machine cycle of the halt instruction. Fine. So as soon as we basically write halt instruction, it has its own micro RTL, it enters its opcode fetch machine cycle, and in the T4 state halt becomes equal to 1. So once halt becomes equal to 1, that is this instruction becomes equal to 1. So what happens is it basically sets the halt flip-flop of the microprocessor. The halt flip-flop is set inside the 8085 microprocessor upon after the execution of T4 state of the opcode fetch machine cycle of this halt instruction. And as soon as the microprocessor basically enters the T1 state of the next machine cycle, the microprocessor basically will will now check the status of the halt flip-flop, and if it sees that halt is set to 1, the microprocessor enters into the halt state. If it is not equal to 1, if it is reset, so microprocessor will not enter the halt state. So after in the T1 state of every other in the T1 state of the next machine cycle, basically the microprocessor will enter the halt state. Fine. So we are say for example, this will happen in case of this will basically be checked in case of every T1 state. After every T1 state, the halt flip-flop will be checked. If it is equal to 1, if it is set, then the microprocessor enters the halt state. If it is not set, it will not enter the halt state. Fine. So once only execution of halt instruction will make sure that the microprocessor enters the halt state, and once in the halt state, the microprocessor basically does nothing. So how can we so once the microprocessor enters the halt state, it will continue to remain in this state, but it will keep on checking the value of one. It will keep on checking the value of interrupt, and it will keep on checking the value of hold. Fine. So there are only three ways for the microprocessor to exit the halt state. What are the three ways? One is reset in is your pin. If this is set to 0, that means actually active low. If this is set to 0, the microprocessor enters the reset. Microprocessor basically reset, and it enters the T reset state, and it exits the halt state of the T halt state. Second way of getting out of the halt state is to make sure that the hold signal is high. If the hold signal is high, the microprocessor will enter the hold T hold state and exit the T halt state. Fine. So you can exit the T halt state by either setting it into T reset state, or you can exit the halt state by setting it into T hold state. Or third way of exiting the T halt state is by execution of the interrupts. So if your interrupt is actually enabled, previously the interrupts were enabled, EI flip-flop, INT flip-flop was set to 0, was set to 1 by any interrupt that the INTA flip-flop is set to 1, that means your microprocessor will exit the T halt state. So if int is equal to 0, if hold is equal to 0, it will continue to remain in the T halt state. But if if reset in becomes equal to 0, that means it's active low, it will exit out of this and enter the T reset state, or it can enter the T hold state if hold becomes equal to 1, or it can execute an interrupt if INT flip-flop becomes equal to 1. INTA flip-flop becomes equal to 1. So in three cases, the T halt state can be exited by the microprocessor. Either it's resetting the microprocessor, or by entering the hold state, or by entering the interrupt acknowledge state. And during the time the microprocessor in this hold state, there's actually nothing that the microprocessor does. It's actually in the idle condition. And halt, the microprocessor will enter halt upon the execution of T1 of the next machine cycle. Fine. So it will actually start executing the next machine cycle. Say for example, I have written halt instruction, its opcode fetch machine cycle is over. So that means my program should have entered the halt state, but it will enter halt state only after execution of T1 of the next machine cycle. Fine. So this is about the T1 state, the T halt state. Next, we'll be discussing now the T wait state. So T-wait state, we have talked about T-wait state in case of I/O devices, wherein we said that a microprocessor will have to uh, a microprocessor when interfaced with an external device in an I/O device may have to wait for the device to be ready for transfer of data. So during the time the microprocessor is actually waiting for the IO device to react, the machine enters the T wait state. So for external IO devices or in for accessing the memory of the microprocessor, uh, slow processing may be involved. So we know that the microprocessor, if it's case of a IO read machine cycle or a memory read machine cycle, in the T2 state the read signal becomes active by making it actually equal to 0. So as soon as the read signal is active, the microprocessor starts reading the data from the memory or from the IO device. If the IO device is not in sync with the microprocessor or the memory is actually not in sync with the microprocessor, so what happens in case of T2 state, as long as the data is being actually read completely, the microprocessor may enter the T wait state. Fine. So from T2 the microprocessor may enter the T wait state as long as this ready is equal to 0. So as soon as ready becomes equal to 1, that means now the microprocessor has been told that the IO device or the memory is ready now for transfer of data. So upon execution of the ready state, the microprocessor will enter the T3 state. So before actually entering the T3 state, the microprocessor basically checks the whole flip-flop between the T2 and the T3 state. So this is the T wait state. Slow processing IO devices or memories can result in the microprocessor can actually make sure that the data bus until the data bus basically reads the data completely, the microprocessor enters the wait state, and this number of cycles depending upon the IO device how slow it is, the microprocessor will continue to remain in this state, and only after execution of upon successful execution the microprocessor will come out of this T wait state by checking the ready signal. And during this time all the buses basically are kept on hold. Only the data bus is in wait of the data. Next, we have the T hold. So when does a microprocessor enter this T hold state? It can happen if an external device, if a External device is actually wants direct memory access. We have already talked about the DMA. So that and we have discussed DMA is actually used for fast transfer of data between the external device and the memory directly. So during this state, the microprocessor enters the hold state. Uh, so during DMA, direct memory access operation, the microprocessor enters this state. So as long as the external device is in communication with the memory, the microprocessor will continue to remain in this state, and it will take up integral number of uh, clock cycles. Now when is this state checked? It is checked after T2 state and after T4 state of each machine cycle. Fine. If a machine cycle has T4 state, then it will be checked twice. If the machine cycle has only T3 has only three T states, T1, T2 and T3, then in that case the microprocessor will only check it once in that machine cycle, in that particular machine cycle. If you are talking about memory read machine cycle, say for example it has only T3, T1, T2 and T3 states. So after T2 state, the hold flip flop will be checked, and it will be executed if hold flip flop is equal to 1. The microprocessor enter will the T hold state, or it will be so after every T2 state, after every T4 state, the hold flag is checked. Also, the hold flag is checked when the microprocessor is in the halt state. We have also discussed that. From T halt, the microprocessor will check and acknowledge whether hold is 0 or not. So this is T hold, T wait, T halt. Then you have T reset. The microprocessor by default is in this state as soon as you reset the microprocessor. So in this state, the microprocessor is basically actually waiting for the instruction to execute, and it will continue to remain in this state as long as the microprocessor is not as long as execution of program is not pressed, or we have to execute the program. Only upon execution of the program, the microprocessor will exit the T reset state. So this state is the default. By default, the microprocessor will enter this state, and it will continue to remain in this state as long as reset in is not equal to 1. Fine. So after reset in becomes equal to 1, the microprocessor enters the T1 state of the machine cycle. Now we have discussed about these four T states, T1 to T6. We already know for every instruction what takes place in T1, T2, T3, T4 and T5 and T6 states. Now what does the state transition diagram basically give us? It gives us how the microprocessor exits one T state and moves on to another T state, and how long. It basically also gives us an idea about from which T state the microprocessor enters to another T state. It's not that the microprocessor will directly enter the T hold from T1, or it will enter T wait from T3. This is not going to happen. If the microprocessor has to enter the T wait state and it's executing T3 state right now, it will only take place in the next machine cycle. So this is the complete I'll be showing you the complete state transition diagram of microprocessor 805. So this here is the complete state transition diagram of microprocessor 8085. So you can see the microprocessor is in the T reset state here. As long as reset in is equal to 0, so it will remain in the T reset state. As soon as reset in becomes equal to 1, that it's actually low when reset in is equal to 1. Thereafter the microprocessor enters the T1 state. From T1 state the microprocessor may enter the T halt state if previously the halt instruction was executed. If previously the halt instruction was not executed, the microprocessor will go on to the T2 state of the present opcode fetch machine cycle. In the T2 state, the microprocessor, if it is ready, it will move on to this path. Fine. If it is not ready, that means we are actually performing some IO operation where our device is not actually yet ready to transfer the data. Ready is equal to 0. The microprocessor enters the T wait state. Fine. And the microprocessor will remain in the T wait state as long as ready is equal to 0. As soon as ready becomes equal to 1, the microprocessor leaves this, it rejoins this path, and as I said to you, after every T2 state the microprocessor first checks whether hold is equal to 1 or not. If it is equal to 1, it will enter the if it is equal to 1, it will enter the hold T hold state. If it is not equal to 1, it will enter the T3 state. Now for if the microprocessor, if it is the first opcode fetch machine cycle, then in case of opcode fetch machine cycle you have T4 state, it will go into this path. If it does not have a T4 state, it will go through this path. Fine. So once it enters the T4 state, it will then check whether the hold is again equal to 1 or not. If it is not equal to 1, it will enter the T5 state. If it has to enter the T5 state, or it will follow this path, and so you can actually see that all those cycles, all those machine cycles, that only consists of T1, T2, T3. After that we need to go to the next machine cycle. Now if it has T4, if it has an opcode fetch machine cycle that has only T1, T2, T3, T4, it will rejoin that path. But if it has T5 and T6 additionally, we have seen some opcode fetch machine cycles where we had T5 and T6 also, then T5 and T6 state will be entered, and then the microprocessor will back follow this path. After this path, what happens is that again the hold flip-flop is basically HLDA flip-flop is checked whether it is equal to 1 or not. If it is equal to 1, it enters the T hold state and remains in this T hold state as long as hold is equal to 1. If hold is not equal to 1, it will exit this T hold state. This is here, this is check last machine cycle. So in each instruction there can be number of machine cycles. If it is the last machine cycle of this instruction, then what happens, it will check whether interrupt is equal to 1 or not. If it is not the last machine cycle of this instruction, then it will go back to the T1 of the next machine cycle. Fine. If it is equal to 1, it will enter it will check whether interrupt is equal to 1 or not. If interrupt is equal to 1, then what happens, it will enter the interrupt will be basically executed. If it is not equal to 1, then it will again go back to the T1 of the next machine cycle. In any case, it has to go to the T1 of the next machine cycle, and after execution of T1 only, it will check whether it has to go previously, depending on the previous instruction, it will enter the halt state or not. So this is your halt state. So you can enter the halt state only after execution of the T1 of the next machine cycle. So if the next machine cycle, depending upon what the previous instruction was, the machine may enter the microprocessor may enter the T halt state or may not enter the T halt state. And you can also see what the microprocessor will remain in the T halt state as long as interrupt is equal to 0, hold is equal to 0. It will exit from the T halt state only if reset in becomes equal to 0 or hold becomes equal to 1. Then it will go from this path into the T hold, or it will check whether interrupt is equal to 1, then it will basically acknowledge the interrupt, and accordingly the interrupt will be first of all executed. And upon execution of the interrupt, what happens is the microprocessor will enter the interrupt acknowledge machine cycle. So interrupt acknowledge machine cycle will have its own opcode, will have its own T1, T2, T3, T4 states. So it will again go back to the T1, T2, T3, but depending upon whether it's in what the previous instruction is. Fine. So this is the complete state transition diagram, how the microprocessor 8085 moves from one T state to another T state, how it basically remains in the T hold state, how it remains in the T halt state, how it remains in the T wait state, and how it remains in the T reset state. So this completes our state transition diagram. You should be able to know how the microprocessor basically transitions from one T state to another. So that's all for this session.